Hello. In this video we're going to take a look at quantum superposition. The central story of the video is going to be that quantum mechanics is linear. What we mean by that is that if two wave functions, psi1 and psi2, are independently solutions to the time-dependent Schrödinger equation, then any linear combination of them also does. That is, wave functions obey linear superposition. In general, as we saw in a previous video, we can write the following. If we can write some arbitrary wave function down, we can decompose it in terms of energy eigenstates, psi n, and any linear combination like this will also be a solution to the Schrödinger equation. So it's not just a sum of two, it's a sum of any number of wave functions which individually solve the time-dependent Schrödinger equation. Let's clear the board, just move this up to the top. And just to reiterate, if psi n is a solution to the time-dependent Schrödinger equation, then any arbitrary function which is written as a superposition, a sum of different psi n's weighted by coefficients fn, which are in general complex, this is also a solution. These are energy eigenstates that we've been dealing with so far. If we perform a measurement on f of x and t, a measurement of energy, this is where things get a little bit strange in quantum mechanics. We will always find exactly one of the energy eigenstates. So let's write that down. A measurement of the energy of f of x and t will reveal one energy En. So even though we prepared the state in a superposition of different energy eigenstates, when we make a measurement of the energy, we only find one of the energies. And as a result of that, the wave function will change as a result of that measurement. It will no longer be f of x and t, it will then be the energy eigenstate corresponding to that eigenenergy. After measuring energy eigenvalue En, the state is psi n x and t. And that's with certainty. Whether you want to say that the state has changed depends on your interpretation of quantum mechanics. In the standard interpretation we tend to teach in university, the Copenhagen interpretation, this process is called wave function collapse. But this is an interpretational question. In the many worlds theory, for example, wave function collapse does not exist. There is a different process for explaining how a state prepared in f of x and t can, when measured according to its energy, changes into psi n of x and t. In fact, it doesn't change, it just appears to change to us. So the probability for, when performing an energy measurement on f, to find energy En and for the state subsequently to be psi n, is given by the modulus square of the coefficient, assuming this is correctly normalized, which all physical states in quantum mechanics are. The probability to find the result En in an energy measurement of f of x and t is modulus fn squared before the measurement. After the measurement, it will be in state, it'll have energy En with probability 1, so the state really has changed. We'll look at some of the more philosophical interpretations surrounding this in a separate video. For now, let's take a look at what this means for the time dependence of states. Let's just clear the board. So let's take a look at the time dependence. In the absence of measurement, the time dependence of a state is dictated entirely by the time-dependent Schrödinger equation. So we have that the state psi evolves unitarily according to the time-dependent Schrödinger equation in the absence of measurement. The word unitarily here, we'll see in more detail what this means later on in the course, but for now all we need to know is that a unitary evolution of the wave function simply preserves the normalization. If you start with a normalized wave function, which you must for a physical state, it remains normalized for all subsequent times, and this is built into the Schrödinger equation. Okay, so we'd like to look at the time dependence of states. Remember, if we have an energy eigenstate, the probability density of that eigenstate is time independent. So if this is our energy eigenstate, labeled with subscript n, then the probability density is this. So rho n is modulus square of psi n. This is a function of time, but the result is completely equal to phi subscript n, only a function of position x. And that's because of this, the form of the time evolution. However, when we take a quantum superposition of two different energy eigenstates, the resulting probability density need not be time independent. So consider this state, alpha psi 1 plus beta psi 2, where psi 1 and psi 2 are different energy eigenstates. The probability density is this. It's equal to modulus psi squared again, and expanding the product, we find this result. And if we stick in the forms of the energy eigenstates again, we find the result. So it takes this form. From this term here, psi 1 is time dependent, but when we take the modulus square of it, because it's an energy eigenstate, the result is the same as phi 1 squared, modulus which is time independent. Same with phi 2, but the cross terms are in general time dependent. The result is still real because it's a probability density, so it better be real, and we know it must be real because we're taking the modulus square of some number, which is always real. But it may in general be time dependent, even though the states from which it's a sum are separately have separate time independent probability densities. Okay, now let's take a look at the normalization of this superposition. So let's clear the board again. So we'll look at normalization. We'll pick the same state as before, and remember that all physical states must be normalized, which means that the modulus square of the wave function integrated across all of space must equal 1. We ensure that our energy eigenstates are normalized, and so this places a condition on the possible alphas and betas we can take in our superposition. In this case, the condition is this, which equals, again, just expanding the product into these four terms. But we know that not only are our energy eigenstates normalized, they're also orthogonal to one another. So that condition, by definition, means that this term is 0, because this is psi 1 and psi 2 are orthogonal. So by definition, this is 0. Same with this term. And we also have that these two states are normalized. So putting this together, we find the following. That is, 1 equals the modulus of alpha squared plus the modulus of beta squared. So this gives us our normalization that must appear on this wave function as the following. That is, we now have a properly normalized wave function psi for arbitrary complex alpha and beta. If we perform an energy measurement on psi, it's not itself an energy eigenstate. We won't certainly get any particular energy. We can say for certainty that we won't get any result other than E1 or E2 because the amplitude for any other energy eigenstate is 0. It didn't need to be, but it is in this particular choice. And the probability that we'll find energy E1 is given by the modulus of alpha squared divided by the normalization, which would be this thing squared, so it'll be modulus alpha squared divided by modulus alpha squared plus modulus beta squared. And similarly, the probability for finding energy E2 will be the modulus of beta squared divided by the normalization. So this guarantees that the total probability to find the particle in some energy is equal to 1. As always, when we carry out our normalization, notice that the normalization condition only places a constraint on the magnitude, not the phase. So we're left with a global phase, which is again ambiguous out the front of this wave function. But the relative phase between these two contributions to the superposition is important. So that would change things, but there's a global complex phase at the front of this, which is arbitrary, because the global phase in quantum mechanics is unobservable. Okay, thanks for your time.